So in this video, we'll talk about a topic called exact differential equations. But first, we need to go over one particular technical skill, which is something called partial derivatives. This is something you learn in multivariable calculus, so some of you might have seen this and some of you may not have. Now, the idea behind a partial derivative is that in multivariable calculus, instead of having functions like, f of x equals x squared plus x, you might have a f of xy equal x squared y plus 3 cosine of xy. So this is a function of two variables. For those of you who might know this notation, it takes two elements in the reals, and it gives you one element back. This is called a surface. Now, if you want to differentiate f, you see that you have two ways of doing it. To differentiate f, okay, f, you can do so, okay, in terms of either letter of x or y. And so here is the notation. So for example, if I have f of xy equals x squared y plus 3 cosine xy, then this notation here, df dx, right here, this is not the same thing as df dx, right? This is a curly d. df dx is equal to the derivative of this object right here, pretending that y is a constant, right? Y is a constant. So in other words, you can think of, maybe you could put a y0 here or something like that to remind yourself that it is a constant and it is differentiated as if it were a constant. So what is the derivative of this, right? So when you take the derivative with respect to x, then the y is a constant, so it's a constant times x squared. So it's just equal to this, 2xy. The y does not get differentiated. The y just tags along as a constant. Now, the derivative of cosine is negative sine of xy, but you have a chain rule. The chain rule says differentiate this on the inside by x, right, in terms of x. So I have a constant y naught times x. A constant times x, for example, a constant times x, the derivative is just a constant. So here, the derivative, okay, with respect to x is just equal to y. So that is the partial derivative, okay, of f with respect to x. Now, f with respect to y, how would you do that? Okay, so in this case here, the x is the constant. So I'm treating the x like a number. So if x is a number, x squared is also a number. So a number times y, well, when you differentiate that in y, you just get the number, right? Like the derivative of 5x is just 5. So the derivative of x squared y is just x squared. Now, again, the derivative of cosine is minus sine xy, but now you're differentiating the inside with respect to y. X is a constant, so a constant times y, the derivative is the constant, so there's an x here. Now, let's do another example, right? So f of xy equals x plus 3 y squared plus 2xy to the fourth power. So let's differentiate this in x. Well, the derivative uses the power rule, so you just bring down the 4, and you write what's inside the parentheses. You knock the power down to 3, and now you have to take the derivative of the inside with respect to x. So the derivative of x is just 1. Now remember that y is a constant, so the derivative of a constant is just 0. And here, what do I have here? Well, the y is a constant, so 2y is the constant that's attached to x. So the derivative is just 2 times the constant. So that would be the partial in x. Now, what is the partial in y? Okay, again, power law, 4 times x plus 3y squared plus 2xy raised to the third power. Now I take the derivative on the inside with respect to y. So x is a constant. So this x differentiates to 0. Okay, we're differentiating in y, so that's 6y. And again, x is a constant, so that is a constant times y, the derivative is the constant. So here is the partial with respect to y. Now, one interesting result is that, I mean, you can take multiple derivatives, right? You can take double derivatives, right? So let me explain. So suppose I have f of xy equals, say, 3x cubed y squared plus 8xy plus y, right? Now, if I take df dx, what do I get? Right? df dx is, I'm taking the derivative in x, so I get 9x squared times my y squared, which is a constant. And then I'm taking the derivative in x. So y is the constant, 8y. And then I have a 0 here. Okay. Now the thing is, after I take a derivative in x, okay, I could take another derivative in y. So I'm going to take a look at this. All right. I've taken one x derivative. I can take a y derivative now. Now, if I take a y derivative, right, what is my derivative here? It's 2y. So I get 18x squared y. Okay. I'm differentiating in y, so I get an 8. Now, let's see what happens if I differentiate by dy first. If I differentiate in dy, right? So the x is a constant. So I get 6x cubed y that, and I'm differentiating in y. So x is a constant, and then I have a 1. Now, what if I decide to differentiate by y and then differentiate again by x? Okay, differentiate again by, so I'm differentiating this in x. So y is a constant. I have 18x squared y. I'm differentiating in x. So this 8x becomes an 8, and the 1 becomes a 0. And notice that these are the same. Okay. So this is a result called the equality of mixed partials. Okay. The equality of mixed partials mean that if I have a function f and I differentiate it by x first, and then I differentiate in y, it's the same thing as taking f and differentiating by y first, and then differentiating by x. Okay. Sometimes you see this d's put together. So you get a d squared f over dy dx is equal to d squared f over dx dy. And this will show up in our discussion a little bit later. Now let's recall a little bit about the concept of implicit differentiation, right? When you differentiate, okay, a function y equals, say, x squared plus x, right? Then you have y prime equals 2x plus 1. This tells you that, the graph of x squared plus x, whatever it looks like, right? Maybe this, right? At a particular point, say x naught, the slope right here is 2x naught plus 1, right? That's the derivative. But you see that here, this particular y satisfies the horizontal line test. So, right, the horizontal line test, I'm sorry, the vertical line test. The vertical line test says that every vertical line in the plane intersects the function at most one time. So here, right, y is a function of x. But sometimes you have shapes that are not where y is not a function of x. Sometimes you have a shape where y is not a function of x, right? Perhaps our favorite example is a circle. A circle of radius 1 looks like this, right? It does not satisfy the vertical line test because this line, for example, hits the circle twice. And so this is not a function, right? But, you still should be able to find tangent lines at the curve, okay? But you should, okay, still be able to find tangent lines, okay, at various points. And this is where implicit differentiation comes in. This is where implicit differentiation, okay, arises. Now, a differential equation, a differentiation. So basically what we have here, okay, is in effect, we have kind of a function in x and y, right? And then I'm differentiating with respect to x, so what does that look like? So let's just take a slightly more interesting example. Let x squared y plus y squared plus well, let's make it a little bit more benign at the beginning. Plus 4 x plus 3y is equal to 2. Now here, what I want to do is I want to differentiate in x, okay? In x. So if I want to differentiate in x, I get a 2x here. Now you see that there's no x here, right? But you still, because y is actually a function of x, right? Y is secretly a function of x, uh, at least some of the time, right? Not necessarily everywhere on the curve together, but some of the time. So you have 2y, but then you have to multiply by y prime because of chain rule, right? So this y prime, you can write it as dy dx, right? All right, you're differentiating in y, so I'm sorry, in x, so that becomes a 4, and then you're differentiating in y again, so that's 3 dy dx, and then you get 0. So what you want to do is you want to group together the dy dx's into one side. So let's keep these two pieces on the left, and we move the other pieces to the right. And then I factor out a dy dx, 2y plus 3 is equal to minus 2x minus 4. And so dy dx is equal to minus 2x minus 4 over 2y plus 3. Now, let's perhaps do another example of implicit differentiation. Maybe let's try a little bit harder one. Say xy squared plus x squared y cubed plus y squared equals 4. Now you see that if I'm differentiating in x, I have a product here and I have a product here, so I need two product rules. So the derivative of the first times the second plus the first times the derivative of the second, so that's 2y prime, chain rule. And then for this term right here, the derivative of the first times the second plus the derivative of the second times the first. So here's the first times the derivative of the second, 3y squared y prime. And then to differentiate this in x, I get a 2y prime, and that equals 0. So let's collect all the terms with a y prime. There are 3 of them. And let's factor the y prime out. I get 2xy plus 3x squared y squared plus 2y, okay, um, is equal to, and let's move all the other pieces back, minus y squared plus 2xy, minus 2xy cubed. And those are the only terms. So y prime is equal to minus y squared minus 2xy cubed divided by 2xy plus 3x squared y squared plus 2y. Now notice that this is a differential equation, an ordered differential equation. And the question is, how do you actually go backwards and solve for the original problem again? Okay, so the question becomes, okay, solving, right, this ODE requires us to do implicit differentiation, right, backwards. So how does one go about doing that? Okay, so let's take a look at this stage right here, right? Actually, let's just recopy the first two lines. Let's take these, copy, right? And then paste it right here. Now, what I'm going to do is, right, so I'm going to call this guy f of xy. And let's group, again, let's group all these guys over to one side, but let's not move the other pieces to the other side. So I have y squared plus 2xy cubed plus, and then this term 2xy plus 3x squared y squared plus 2y, okay, y prime is equal to 0. Now, the thing is, if you stare at this long enough, right, you'll realize that there's something really interesting happening here. Notice that this was my original f, okay? And here is some term, okay? And here's a term that's attached to the y prime. So I have these two terms right here. Now take a look at this. If you look carefully, you'll see that this guy is the partial derivative of this guy in x, right? So in other words, if I differentiate f in partial way with respect to x, like look at this. So when you differentiate that with respect to x, you get a y squared. And then here, if you do x, you get 2xy cubed, okay? And then here, for x, you get nothing. So this term right here is simply df dx. And, right? And then this term right here, okay, is actually df dy. So this actually looks like this expression right here, df dx plus df dy, y prime, okay? So in fact, the differential equation, okay, the ODE can be solved, okay, by, so let's call this piece M, okay? Let's call this piece N, right? Can be solved by anti-differentiating, right? M with respect to x and N with respect to y. So let's see how we would do it. So here, my df dx is equal to y squared plus 2xy cubed. So I'm going to anti-differentiate this with respect to x. So that means that f, that's anti-different. Okay, so y is a constant. So I get xy squared. I'm anti-differentiating in x. So I get an x cubed y, x squared y cubed. Now I have to add a constant, but this constant, since y is a constant in this particular setup, uh, I could be a function of y, right? Y is a constant. Now, df dy, what was df dy? It's 2xy plus 3x squared y squared plus 2y. So I need to anti-differentiate this with respect to y, okay? Well, if I anti-differentiate this with respect to y, I get an xy squared, okay, plus x squared y cubed. Okay, anti-differentiating in y, I get a y squared. And then I get a constant which may depend on x. So you see that both of these equations have to be true simultaneously, so I do a comparison. So I compare these two, and then these two. Now this guy has an extra y squared, right? But it could be absorbed into this piece right here. And I don't really need that piece because I don't really need it, right? So f is xy squared plus x squared y cubed plus y squared, okay? Which is exactly what we have right here for f, okay? And so our final solution, okay, is xy squared plus x squared y cubed plus y squared equal to a constant. Now our constant was 4, but we can't really recover the constant unless we have an initial condition, okay? So in the absence of an initial condition, so I mean, supposing you just started here, okay, then you'll wind up with without initial condition, you'll wind up with a C. And so here's my C. Okay. All right, so that's the conclusion of that problem. All right, this is working backwards in um, an implicit differentiation problem. Now let's do another example. Let's take a look at this one. This one will have y's and t's on it instead of x's and y's. So 3y plus e to the t, right, plus 3t plus cosine y dy dt equals 0. All right, so let's take a look at this one. Let this one be m, and this one be n. Okay, so we were asking, is there, right, is there an f such that, right, so df dt dt is equal, so this is, right, df dt is 3y plus e to the t, and df dy is equal to 3t plus cosine of y. So if I anti-differentiate f dt, right, with respect to t, I get 3ty. So f is equal to 3ty plus, I'm integrating e to the t with respect to t, e to the t plus a constant possibly in y. At the same time, I'm integrating here in y, so I get a 3ty, right? And then I'm integrating cosine of y, I get, with respect to y, I get a sine y plus a possible c2x. Now, if I compare these two, these are the same, that's good. This e to the t can be absorbed into here. Sorry, that should have been a t right here. And this could be absorbed into that. So basically, f is equal to 3ty plus e to the t plus sine y, right? And the solution is given by 3ty plus e to the t plus sine y, okay, equals c. Now, the thing is, right, now, the thing is that not every problem can be done this way. Not every problem can be done this way. So for example, if I just had like, xy squared plus, say, x plus cosine of y dy dx equals 0. Say I have this, and say I have an m here, and then I have an n here. And then I ask myself, is there an f that can give me this and this simultaneously, right? So in this case, f, I'm integrating in x, 1/2 x squared y squared plus c1 of y. And here I have f equals xy plus sine of y plus c2 of x. And you see that even though this can be absorbed in this, these two equations are completely incompatible. This guy is not showing up anywhere here, okay? So there is no f, right? There is no f, right? There is no f, okay? uh, that that so what are we saying? That this is not the result of an implicit differentiation, okay? So this ODE is not the result, okay, of an implicit differentiation, right? So how do we solve it? Okay, you have to find some other way, okay? But it's not this way. So if such an f exists, if f exists, then the equation is called exact, okay? If not, then it is inexact. So this question up here, right, is inexact, right? And we just cannot do it this way. We have to find some other way of doing it. This problem right here, you see, I was able to find an f, and this guy is exact, and I'm able to do it by anti-differentiation to get at an implicit equation. So not all problems can be solved this way. And so when you're doing problems in the exactness section, you have to try to figure out whether or not it can be done this way, and if not, you have to find another way of doing it. Okay, so so how do I find out whether it's doable? Well, you have to see if there's an f, right? So let's do an example. Okay. So let's say 3t squared y plus 8ty squared plus t cubed plus 8t squared y plus 12y squared, okay, dy dt equals 0 with y of 2 equals 1. All right, so the question is there an f, right? Is there an f that does the following? df dt is equal to this part, 3t squared y plus 8ty squared, right? And simultaneously, df dy is equal to t cubed plus 8t squared y plus 12y squared. So f is equal to, I'm anti-differentiating in t, so I get t cubed y plus 4t squared y squared plus a possible function of y. And f also has to be, okay, I'm anti-differentiating in y, all right, plus t, let's see, 4, yeah, this is also 4t squared y squared, right, plus anti-differentiating in y, 4y cubed, plus possible function in t. And if I compare the two, I see that these are the same, and that could be absorbed into that. So f is equal to t cubed y plus 4t squared y squared plus 4y cubed. And then the differential equation solution, right, the implicit function that we have here is with a c. Now, in this case, we can solve for c because we have an initial value. So for example, at t equals 2 and y equals 1, right, let's figure out what c is. Right? So here's 2 cubed is 8 plus 4 times 1 plus 4 times 1 equals c. That's 8 plus 16 plus 4 equals c. So c equals 28. And our final solution is t cubed y plus 4t squared y squared plus 4y cubed equals 28. Now, there are two ways, right? So let me just mention again. Remember, we were talking about the equality of mixed partials. The equality of mixed partials, okay, says that if I have a function f, right, and I differentiate it with respect to x, and then differentiate with respect to y, this is the same thing as differentiating in y and then differentiating in x, okay? Now, if I have a function f of x, y, right, equals, some c, right, as my initial implicit equation, say, x squared y plus y squared x cubed equals 4, okay? And suppose I differentiate it, so I get by product rule 2xy plus x squared y prime plus 2y y prime x cubed plus 3x squared y squared equals 0. And let's just group this together. So 2xy plus 3x squared y squared plus x squared plus 2x cubed y prime is equal to 0. So this part right here is dx, which I call m. And then this part right here is df dy, which I call n. Now, if I take m, right, if I take this guy right here and I differentiate it in y, that is the same thing as taking the double derivative first in x and then in y. And then here, if I differentiate n with respect to x, that is the same thing as differentiating by y. This is n, and then to differentiate that by x. And I know that these two objects are the same, right? I could write it like this. Okay? And these are the same. So therefore, right, dm dy equals dn dx if this differential equation, m of xy plus n of xy dy dx equals 0, comes from implicit differentiation. Okay. In other words, right? In other words, if, right, this equation star, if star is exact, okay, then dm dy, right, has to equal dn dx, right? So taking the contrapositive, so if dm dy is not equal to dn dx, then immediately star is inexact, and you can't solve it this way. And you cannot solve, okay, by integrating. So here's an example. Take x squared y cubed plus 4y plus 8x plus sine y plus x squared y to the fourth dy dx equals 0. Now this guy is m, and this guy is n. I'm going to differentiate m in y. So I get a 3x squared y squared plus 4. And I'm going to do dn dx. That's 8 plus 2x y to the fourth. I mean, they're absolutely not the same. So this problem, okay, is inexact, and we can't solve it. And we have to find some other way. Okay, we must find another way. Right? And that other way is not the focus of this, but this chapter is about exact, and we're only interested in solving exact problems, right? But here I am, as soon if you do this calculation and it's not and they're not equal, then you can basically say this problem is inexact and we can't do it, but using methods of exactness. Okay. Now, what if they are equal, right? If dm dy is equal to dn dx, right? Then then we can solve for f, right? But then you have to anti-differentiate, okay? So then you need to anti-differentiate. I mean, using this method right here is good, right? Is good when the outcome is not exact. But when the outcome is zero, is exact, when they are equal to each other, then you have to sort of go back and still do the anti-differentiation, because this is not the end of the problem, right? You've shown that it's exact, but you haven't figured out what equation it comes from. So let's consider the following exercise. Let's get some trig functions in here. Y secant squared t plus secant t tangent t plus 2y plus tangent t dy dt is equal to 0. So first, use dm dy dn dx to establish, that this equation is exact, right? Then integrate to find the solution, okay, right, which will be in an implicit form. All right, so let's do A, right? So here's my M, okay, here's my M, and here's my N. Okay, and by the way, it's not dn dx, it's dn dt. Okay. So let's do dm dy, right? Dm dy is secant squared t, and then this becomes 0. Oh, well, that's it. And then dn dt is just the derivative of tangent t, which is secant squared t. So it is exact, right? So that means that I need to be able to find an f whose partial here is secant squared t plus secant t tangent t, and simultaneously the f dx is equal to 2y plus tangent of t. So let's figure out what f has to be. I'm anti-differentiating in t, so I get a y tangent t plus secant of t plus a possible constant in y. Here, I'm anti-differentiating in, let's see, this should be a y. I'm anti-differentiating in y, so I have a y squared plus y tangent of t plus a possible constant. This constant should have been c1. This constant is c2, and it could contain t. So let's take a look at compatibility. Here's my y tangent of t. Oops. And then my secant t can go into here. And then my c1 of y can be that. So my solution is y t plus secant t plus y squared equals a constant. All right, let's just do one more for giggles. Solve the following. Solve t 2ty cubed plus 3t squared y squared dy dt equals 0 with y of 1 equals 1. Okay. So I'm just going to ask, is there f, right, such that, right? I mean, you don't ever have to do this piece right here. Some professors will probably want you to check, but the thing is, you can always check just by integrating and seeing whether or not the uh, the equations that come out are actually compatible with each other, right? So df dt is equal to 2ty cubed, and then df dx dy is equal to 3t squared y squared. So in the first, I have f, right, is equal to t squared y cubed plus a function y. And then here I have t squared y cubed plus a function in t. And you see that they're compatible. So t squared y cubed is equal to a constant, right? And if I stick in t equals 1 and y equals 1, then c is equal to 1. So my final result is t squared y cubed equals 1. Now, in fact, this problem here, you actually can solve for y. So y cubed is 1 over t squared, and so y is equal to the cube root, 1 over the cube root of t squared. Okay. So, and if you stare at this long enough, you'll probably recognize that you can actually even do this as a separable equation, but it turns out to be exact as well. All right, that's the end of this video. We will do more difficult exact equations in some supplementary discussions. Okay.